So Tuesday, we kind of proved that carbon dioxide is not the guilty party when it comes to acid rain. Yes, it can acidify rain, but it doesn't acidify it to the point where the EPA classifies that rain as being acid rain. That is damaging to crops, damaging to buildings, damaging to infrastructure. Okay, so it's going to come as absolutely no surprise that the main culprit for acid rain are sulfur oxides and nitrogen oxides. Okay, so let's revisit a little bit of general chemistry stuff that we learned early on. We didn't really dwell too much on it, but we learned there are only a handful of really strong acids, and HNO3, which is nitric acid, is a strong acid. What was it about the definition of a strong acid that makes it be strong? Do you remember what the particular definition of? Okay. It means this. What's our very definition of what an acid is? What does an acid do?
Was it base, of course?
Mm-hmm. Gives away its H+. So to be a strong acid, you give away the H+, but you do this 100%. That if there is a bottle in lab, all right, let's treat this as an actual question. Here's a bottle in lab, and there is 1 liter of solution inside that bottle. And the label on the bottle, which we believe to be trusted, says that this is 1 molar nitric acid. How much nitric acid is inside the bottle?
1 liter?
There's definitely a liter of solution in there. The label says that in that 1 liter of solution there is 1 mole of nitric acid. How much nitric acid is in solution?
1 mole.
The answer is none. There is no nitric acid in solution because it splits apart completely. Strong acids do complete ionization in solution. So inside that bottle, there is H+ and there is nitrate. I have hydronium and nitrate. I do not have nitric acid anymore. It's gone. Okay, that's what acids do. Acids give away the H+. Strong acids give it away completely. Okay? If I go down 1 to HNO2, I get to be nitrous acid. And nitrous acid is a weak acid. All right, so the definition of a weak acid is, the definition of a strong acid is an acid that dissociates completely, ionizes completely, deposits all of its available H+ into solution. Guess what a weak acid does?
The opposite?
Yeah, just doesn't go completely to the right. This is the left, that's the right. Reactants, products. So a weak acid sets up an equilibrium. And weak acids have Ka values, the acid dissociation constant, where this value is much, much less. Really, it might only be fractional of a percentage. Only a little bit of H plus comes into solution. Okay, so these two acids are not the same as each other. If I have a mole of nitric acid, I have a mole's worth of acid to give away. This being the acid part. But if I have a mole of nitrous acid, it doesn't give me a mole of protons, of hydronium ions. It doesn't. It gives me much less. Much, much less. Okay? So, and the same is true for the other one. Let's write them all on the board. H2SO4, sulfuric acid. Strong. It does this. Oh, now, there's a little bit of information to be had here, because high school chemistry books and books that are aimed at a non-scientific level get this wrong all the time. Sulfuric acid is a diprotic acid. It has two H plus ions to give, but it gives them in stages. And the first one, only the first one, is given away completely. The second one is subject to resistance, because now I have to remove an H plus away from something that's already negatively charged. Okay, so this one goes 100%. What was the word that we gave to dissolved ions? Ions in solution. It's the Gatorade word.
The Gatorade word.
Gatorade. There's electrolytes. These are ions, and they're dissolved in solution. These are electrolytes. Okay? If you're a dissolved ion, you're an electrolyte. The difference between being a strong acid and being a weak acid is the amount of electrolyte that it puts into solution. This one gives me lots for the same concentration. This one gives me very little for the same concentration of the initial acid that I start with. Okay. The difference between nitrous and nitric is one oxygen. The number of hydrogens is the same, the number of nitrogens is the same, but the number of oxygens is one less. Us means less than ic. Ic means more than us. So this is now sulfurous acid. And it's a weak acid. We have a very, very short list of acids that we call strong acids. They're hydrochloric, hydrobromic, sulfuric, nitric. And then like perchloric acid, which is an acid that we won't ever let you use because it's dangerous. So now I have H2SO3, and it's in equilibrium with H plus and HSO3 minus, the hydrogen sulfite. And again, this is much, much less than 100%. We give weak acids an acid equilibrium constant that expresses products divided by reactants. And those values, it's not uncommon for them to be 10 to the negative 8, 10 to the negative 7, so like 1 for every 10 million of these, you get 1 of those. Okay, so really, really undissociated versus very, very highly dissociated. This is the difference between strong acids, weak acids. Again, ick has more oxygen than us. And it's a simple rule of thumb that the more oxygen your acid has, the stronger that acid is. Okay? All right. So having proven on Tuesday that it wasn't carbon dioxide that was causing the acid rain, today we're going to look at these two. We'll specifically look at this one, because this one's more of a problem than that one. Okay. Strong acids versus weak acids. Are you familiar?
So, I remember talking about them.
Strong acids completely dissociate. They give away lots of H+.
Okay.
Weak acids don't. It's still on the board. This one is a strong acid. It splits apart completely.
Okay.
Completely. This one is a weak acid. It's only different. These two are only different by 1 oxygen. This is where we're going to spend the rest of the day looking at the change from going from here, where I've got an acid, to there, oh, I've got a really good acid, is profound.
Okay.
Anything that puts H+ into solution gets to be an acid. But if you do it a lot, then you get to be a strong acid. I'll write this back up now. Okay. If we're tracking the origin of how did the sulfuric acid and sulfurous acid get into the atmosphere, well, we're going to track it back through sulfur dioxide. The sulfur is in coal. And oil, and to a lesser extent, natural gas. Natural gas is much cleaner than coal and oil. And sulfur plus oxygen. Sulfur is a solid. Oxygen exists naturally as a gas. It's an element. Sulfur is an element, oxygen is an element. Sulfur exists. Its most common allotrope is 8 sulfur atoms stuck together in a ring. It's an octagon. And have you ever seen sulfur? You know what it looks like?
I'm sure I've seen it before.
It's a yellow powder. It's just very, very powdery. And it's yellow, bright yellow. Oxygen is gas, comes supplied to us in nature as O2. Those two just come together and do a combination. Combustion reactions are types of combination or association reaction where you just stick the atoms together. Okay, Well, this is SO2. This is going to be the most common pollutant, and it gets into the atmosphere because it's in fossil fuels, mostly coal. We talked on previous days about ranking coal, anthracite being the best, bituminous being somewhere in the middle, lignite being absolutely terrible. You would only use that as a last resort. We also count the percentage of sulfur that's in coal, and we rank oil, crude oil that you buy by the barrel, as being sweet if it's low in sulfur, or sour if it's high in sulfur. So before you go out and you buy a ton of coal, you wouldn't just pay any amount for it. You would look at the market price and you would find, am I overpaying for my coal? Because I want to know how much sulfur is in it. I don't want to buy dirty coal. Curiously, some coal is cleaner, okay? Doesn't have so much particulate matter, has a lot of carbon, burns cleaner. And that varies geographically. Some places it's really clean, other places it's really dirty. You pay a premium for the clean stuff. All right, let's look at this. If I take sulfur dioxide as a gas and I dissolve it in water, I'm thinking back at this is a reaction that I did in school, probably about age 13. We had these special containers, they're long, tall glass tubes, and we had, it's called a deflagrating spoon. It's a spoon that's on the end of a long stick. It's just a little cup. And it has a lid. And you put the sulfur in here, and then you set it on fire. So outside of the tube, you put the sulfur in the lid, you set it on fire, it burns with a blue flame, and then you lower the lid, and there's oxygen in here. Or when you put some water in the bottom, and the sulfur burns with the blue flame and turns into sulfur dioxide because it's combining with the oxygen, and then that sulfur dioxide dissolves in the water and turns this. Let's do the balance. 1 sulfur, 2 oxygens, 2 hydrogens, and then another oxygen. When sulfur dioxide dissolves in water, it makes sulfurous acid. Modern day chemistry labs don't have very many open flames in them, but we could absolutely do this experiment. I just remember the cleanup from this being nasty, that the burnt sulfur was tar, just nastiness. Okay. And what do we know about sulfurous acid? It's a weak one. Okay. So it's a weak acid. But it is stronger than the acid that we looked at on Tuesday. It is stronger than carbonic acid, the acid that we get when carbon dioxide dissolves in water, H2CO3. And we said that the maximum pH that carbonic acid could deliver was about 5.5. On our pH scale. So here. And we just call that natural rain. The rain that dissolves carbon dioxide has a pH of 5.5. Out in the countryside. Out in the countryside where the air is clean, the rain is acidic to the value of about 5.5 because it's dissolved carbon dioxide. Sulfurous acid would put the value, actually I have the value. The maximum pH that we can get is 4.5. So from carbon dioxide is there, and then from SO2 is here. The lower the pH, the more acidic you get. What was our threshold that we said on Tuesday that the EPA considers to be acidic enough to be classified as acid rain? We put a number to it. The EPA had a number.
For the pH,
Yeah.
it was 4.4.
Yeah. Is 4.4 more acidic or less acidic than the 4.5 that sulfurous acid is going to get you? Yeah. So so a smaller number, more acidic. The most acidic is going to be 0. If you get to 0, that's, oh wow, you're acidic. 7 is neutral. So sulfurous acid pushes the needle right into danger territory. But in order to get damaging, we need to push a little bit more. So the sulfurous acid contributes to acid rain in a significant amount. Not going to under describe its significance. But if we just tweak this a little bit, if SO2 gets oxidized to SO3, it turns out to be possible. It's in the lab, it's a piece of cake, but out in the atmosphere, it's a little bit problematic because, you know, we can up concentrations in the lab and we can add fire and stuff like that, stuff that you don't get in the sky. But if the SO2 that's making this weak acid could get oxidized up to SO3, then sulfur trioxide plus H2O. I have one sulfur, 1, 2, 3 oxygens, 2 hydrogens, a 4th oxygen. Then I make H2SO4. And that is a strong acid. And it's going to contribute So even if the air is clean, rain is acidic, it's naturally acidic to here because it has dissolved carbon dioxide. If the air is polluted because of chimney stacks for power plants, for factories that make things, for car exhausts that burn gasoline that didn't have all the sulfur removed from it, then sulfur dioxide pushes us right into the danger part. That I have absolutely no room for anything else before it gets to be damaging. And then if a small amount of sulfur dioxide gets turned into sulfur trioxide, I scoot way down on the pH and turn from being weak acids into strong acids, and it has a big effect on pH. So this conversion doesn't have to be going on at a large scale. If just a small percentage of sulfur dioxides gets turned into sulfur trioxides, bam, you have acidity. Okay? So let's look at how this happens. And then our book goes through, well, what should we do about that? How should we legislate it? And it's stuff we've already talked about. Clean Air Act pretty much takes care of most of it. Our book tells us a couple of dates, shows us some graphs, and then tells us, oh, Clean Air Act. So if you type in Clean Air Act, the top, your number one search is the EPA. And if you go, you click on it gives you just a couple of paragraphs, but you can click a couple of extra things. And it's good. It tells you exactly what you need to know. But number 2 on the list, if you search for Clean Air Act, is of course Wikipedia. And Wikipedia is complete junk for a number of things. But for sciences, it's actually pretty good, because there's not a lot of arguing over. I mean, I haven't ever looked at Donald Trump's Wikipedia page, but I'm sure that every time somebody makes a change to it, somebody else changes it back, because it's contentious, right? Well, what was written in the law has been written. What is science is science. There's not a lot of people arguing over it. So the Wikipedia page tells you everything that is in the EPA pages, actually using the same words. They've just cut and paste out of the EPA's website. But instead of having to go to a page and click through it to get to other pieces of information, it's all just on one page. Turned out to be quite good. Let's see, how does the SO3 get here? So the naming of covalent molecules is a little bit different than the naming of ionic molecules in terms of, hey, I have magnesium oxide. Well, magnesium's in group 2. It has a fixed oxidation state. Oxygen makes oxide. Group 6 has a fixed oxidation state. But some of the non-metals, and some of the metals, in fact, have variable oxidation states. And so you can get SO2, SO3. You can get N2O, NO, NO2 differences. So we typically don't just call this sulfur oxide, we name the number of oxides there are. So this is sulfur trioxide, and it's you want to be specific. These are all going to start with the same reactants. This is paths from sulfur dioxide to sulfur trioxide. There's a couple of different ways that this can happen. In water droplets. So this happens at the cloud level. It can also happen at the ground level if there's fog. One of the things we could have mentioned on Tuesday, when we were talking about gases dissolving in liquids, is we could have talked about Henry's law. Henry's law is a callback to chemistry 2. We saw it very briefly, and we outlined why we weren't going to use it very much in chemistry 2, because it's clunky. Do you remember Henry's law at all? Henry's law says this: S equals Kp. S is solubility. Now we're going to be specific. S is solubility of a gas in a liquid. K, or sometimes you could put the H there for Henry, is a constant. And then P is the pressure of the gas. And Henry's law has its uses, but all of those uses are very, very narrow. They're very specific, because this constant describes, this is a very vague statement, that constant describes the solubility of a named gas in a named liquid. So this could be the solubility of sulfur dioxide in water. And when you name that specific, that value of K does not work for any other gas-liquid combination. So if I know what the value of K for sulfur dioxide dissolving in water is, I cannot use it to tell me how easy carbon dioxide dissolves in water, because they have different Ks. But once I know the value of K, then I do something that is readily, like abundantly obvious. Solubility and pressure are both on the same line. So when this number gets big, that number gets big. Let's say that the other way. Cause, effect. When you provide me with more gas, I will dissolve more gas. The solubility goes up when you provide the liquid with more gas. Okay? That's Henry's law. But again, it has to be, it's the pressure of a gas in a liquid, and you have to specify, not in liquid, is the pressure of that particular gas. So Henry's law is so completely specific that its application is limited. There's a use of it in the book here about one of the factors that's going to make this happen. From SO2 to SO3, we're adding bonds to hydrogen, which makes this reaction you're increasing the number of bonds to oxygen. It's an oxidation. If you increase the number of bonds to oxygen, that's known as an oxidation. And the reagent that causes an oxidation is given generic symbol O inside square brackets. O is called an oxidizing agent. All right, so I'm going to write this down wrong, and then let's see if we can figure out how to fix it. Here's sulfur dioxide. It's a gas. It's going to dissolve in a droplet of water. Maybe. But the mass balance here says I can only get to sulfurous acid. That's the weak acid. That's not gonna make it. What I'm gonna do instead of this being H2O, I'm going to have this be H2O2. H2O2 is a common household chemical. You can go down the street to the CVS and buy this right now. What's H2O2?
It's 202. The name?
Mm-hmm. That's hydrogen peroxide. And water. Looks like that. It's bent in shape, it's tetrahedral center carbon right here that, just carbon, oxygen, that has two lone pairs of electrons, two covalent bonds, and because its electron geometry is tetrahedral, cannot be linear. Peroxide looks like that. Oxygen, the molecule that's in our gas that we talked about at the very beginning of the term, looks like this. It turns out, we shouldn't talk about atoms and molecules in terms of what they want, because they're inanimate objects, but if an arrangement of electrons is high in energy, it means that that molecule is unstable, it's reactant. And it's kind of simple just to say, oh, the molecule doesn't like it, doesn't like this arrangement. Okay, bearing in mind that molecules don't like stuff. This water is a super stable form of oxygen. Oxygen loves this. This is a super stable form of oxygen. Oxygen is very, very content being in this form. This is why there is so much of these two on this planet. They're both wildly abundant because they are very stable. This, however, is very unstable. An oxygen to oxygen single bond is not a good bond. Double bond, good bond. Two single bonds to something else, good. But a single bond to itself is unstable, which means this is reactive. And it's reactive in a very, very special way. That bond has to break. And the simplest way of making it break is to form it back into water and to let that oxygen go and do something. This oxygen is going to go off and bind to something new. And the thing that it's binding to is going to discover, oh, I have more bonds to oxygen than I used to have. I've been oxidized. So this is an oxidizing agent. Peroxide is an oxidizing agent. There is another molecule that can play a part here. O3, ozone. The square brackets O. Did I write it down? No, I didn't. I'll write it down now. Square brackets O is the oxidizing agent. Ozone can also act as an oxidizing agent, especially, now it's not likely to do it on its own, but if there is a co-reactant, and that co-reactant is usually a metal, the big two being iron or manganese. We don't see a lot of manganese around in general conversation, lots of iron. If we were to count, hey, what's the most abundant atoms on this planet? What is the most abundant element on the planet? Get your Google out and look it up. Most abundant elements on the planet are things that we don't think about a lot.
It says iron,
There's a lot of iron on this planet.
and oxygen.
There's a fair amount of oxygen too.
It says iron, oxygen, silicon,
And then silicon
and
and aluminum and what?
magnesium.
Magnesium. Okay, there's quite a lot of magnesium tied up in life. Yeah.
Yeah.
And aluminum's on that list as well. So the aluminum and the silicon that we don't think about, they're under our feet. They are sand. They're around us. They're in the stones. There's plenty of iron. Our planet actually has a molten iron core, and we have iron oxides as minerals all over the place. And then there's biological iron as well. So to think that I could have a couple of particles of dust in the cloud that contain iron. How unreasonable is that? Every other year, you go outside in the morning and your car's completely covered in dust. Ever this happen? And that dust is red. Where did that come from? The Sahara. The dust, which is full of iron, which is why it's red, blows up from a desert somewhere, and then it crosses the ocean. Big warm storm somewhere over on another continent completely. And then the cloud and the storm travel thousands of miles until the altitude changes and the temperature changes, and then it drops it in rain and deposits it on your car. And now your car has to go get washed because it was out for the wrong couple of days, and it now has red dust all over it. If it's red, it contains iron. Okay. So it is not unreasonable that your cloud could contain particulate matter that is rich in iron, that acts as a catalyst to allow the ozone to do this. The sulfur dioxide becomes sulfur trioxide, dissolves in the water, becomes strong. It's a strong acid. That's one way. There's a couple of others. Oh yeah. In the gas phase, so this one doesn't revolve around anything dissolving and anything else. This now needs the gas particles to bounce into one another. And as I write a couple of equations on the board, there's going to be a cheat of, well, maybe they didn't need to bounce. Do we all know what hydroxide is? Hydroxide is this ion. Okay, here's how we get there. What group is oxygen in? There's a periodic table at the back of the room. Let's go pull it down and see. This has the up-to-date numbering system. Our old numbering system has oxygen group 6, not 16, because the old system doesn't count the 10 in the middle. Okay. 6. Okay. And if you're in group 6, how many valence electrons do you have? 6. Here they are. 1, 2, 3, 4, 5, 6. As you go around and you go past 4, you have to start doubling those electrons up, because electrons live in orbitals, and you can have a maximum of 2 electrons per orbital. I've got 6 electrons to go into 4 orbitals. One is called 2s, one is called 2px, one is called 2py, one is called 2pz. There are 3 p orbitals and 1 s orbital. Okay, that leaves me 2 unpaired electrons. Unpaired electrons can meet other unpaired electrons and make covalent bonds. 2 electrons shared between 2 atoms. Here's what we're going to do. So we just made water. We're going to split this molecule. And I'm going to break it there. So the hydrogen leaves without any electrons, and the oxygen leaves with all the electrons that it had, plus the ones that it was using to bond, plus one that belonged to the hydrogen. That one right there, this one, makes this have a negative charge. That electron used to belong to this hydrogen atom. This is called heterolysis. Heterolysis or heterolytic cleavage is when you break a bond unevenly. When you break it unevenly, one of the atoms gets the electrons and the other atom gets nothing. Now oxygen's on the right-hand side of the periodic table, so it's electronegative. It gets the electrons. Let's do that again, but differently. So this is called heterolysis. Hetero means different. Lys means cut. So this is, we're going to cut it into uneven portions. The round circles are the electrons that belong to the hydrogen. The dark circles are the electrons that belong to the oxygen. I'm going to break that bond again. Only I'm going to break it this way. Down the middle. And I'm going to break this evenly. But now one atom gets one electron and the other atom gets the other electron. So this is homolysis. This has a charge and that has a charge. These are ions. Ions are charged atoms. These two at the bottom, from the homolysis, the even breaking of the bond, these guys are different. They are radicals. What is it that you have to have in order to be a radical? We did mention it once before. A long time ago.
Has to be unpaired.
Yeah. Radicals have unpaired electrons. And that makes them be reactive. That right there is the unpaired electron. Okay, so when we say hydroxide radical, and you go, I know what hydroxide is. That's hydroxide. Well, yeah, it is, but that's not what we're talking about today. We're talking about this. It has an unpaired electron. Now, the actual path of the first one, he said, hey, how does the SO2 get to be SO3? And then we didn't show it. The actual answer is, it's not likely to happen at all. It's more likely to happen somewhere else. The amount of spare oxygens that are around in the atmosphere make straight SO2 to SO3 unlikely. It's going to be through one of these three other things instead. It's an indirect. Okay. Oh, I don't like this. Oh, I know what they're saying. Okay. So I wrote it down differently than the way that it was in the book. I'll tell you where it is in the book. And now, thinking about how to put that in context, it needs to be the way that they say it, not the way that I would say it. So this is on Oh, while I'm flicking through the book, I am reminded that if you do go to the EPA's website, they have some interactive things. They have a graph of others. They have a graph of, hey, here's a map of the United States, and every dot is a polluting center. And if you move, there's a little thing that you're allowed to move, swipe left or right. And as you move, it changes the year. And you can go from being in the past to being in the present. And the size of the pollution like shrinks down. It's kind of cool. What page? Did you find it?
I believe 110.
110, I went, I have to go back. I wasn't thinking I would have to go back. I was thinking I would have to go forward. Yeah, that is one way. I think if you read that, that's an industrial one. Never mind, I'll just write out what I've got. So instead of writing, all right, there's a hydrogen radical right here. You know, that has to be wrong. That has to be a hydroxide. Dot OH. I'm leaving a space here because there's something that I'm going to come back and add that assists this reaction. It's not strictly necessary, but it's going to assist. And then that goes to HOSO2. Which is another way of saying H2SO3. And then HOSO2 plus an oxygen goes to HO2. And there's your SO3 coming out at the end. This first step is slow. Oh, so to go from SO2, here's my reactant. To go to SO3, there's my product. It's a two-step process. What's the role of this guy? That's a callback to a previous week. It gets made in the first step and then consumed in the second step. What's that called? So it never shows up in the final answer. That's a reactive intermediate. Okay. This guy. There is an assist to be had here. Doesn't affect how to balance this equation. But if you have, again, if you have a surface that this reaction can happen on, like a metal, then this reaction works better. Here's a gas. These two particles are a long way away from each other, and they're traveling in different paths. It might be thousands upon thousands of attempts before they ever meet each other. But if there's a piece of dust, then that gas can get stuck to it. And this gas can get stuck to it. And now they're close enough that they can react without having to bump into each other. So this gets to be a catalyst. If there's dust in your gas, for example, you up the chances of this reaction working. And of course it comes out at the end untouched. This reaction is most likely to happen right here in order to generate that radical. That radical is probably generated during sunlight hours. So this doesn't work when it's cold and dark all the time. Doesn't work in winters in northern places. That's why it's second on the list. And then third on the list we've already done. It's this part as well. Okay. If you have particulate matter like soot, here it is. We've just done it. This gas can attach to it, and then another gas can attach to it. And now I have a low energy reaction. I've lowered my activation energy. Reactions that happen on surfaces are well studied and well understood. They are a bit more difficult than undergraduate textbooks can do. All right, let's just close this out. There's loads of legislation that has been used to clean the air specifically to get sulfur dioxide out. And if you read through the book, after it gets out of the technical bits, we find, oh, it mentions this treaty, Gothenburg Treaty, it mentions that one, it measures what Europe did in 1988, it measures this, it measures that. But the one that you're gonna, that's kind of it's the big one, is the Clean Air Act. And the Clean Air Act came in a couple of phases. And I started reading the book, and then I thought, I better just go to the EPA website, because that was written a couple of years ago, and let's just see what the EPA said. So I pulled this from the EPA. It's not going to be different than what it says in the book, and it isn't different than what it says on the Wikipedia. This is Title 4 of the Clean Air Act, includes something called the Acid Reduction Plan. And that comes in two phases. Phase 1 and Phase 2. Now, to write a bill and have that bill become law takes time and influence. And some of these things get argued over, that one side says, no, it's not an issue. So once one side picks, hey, I think we should do this, then the other side just reflexively says, no, we shouldn't. When we all know that we probably should. So what Phase 1 does in 1995, it just starts working on things. And it gives you two numbers. That there are a number of sources of pollution at numbers of sites. Well, why are they not the same number? Well, a power station might have 4 chimney stacks and 4 separate buildings. So one site has 4 sources of pollution, okay? But they took 110 sites and they said, you have to reduce your emissions. These initial sites are coal burning power stations. Because that's where most of the sulfur comes from. As the demand, and we talked about this a couple of days ago, as the demand for coal is gone off a cliff, the amount of coal being consumed in the West is really, really small now in comparison to where it was decades ago. As the demand for coal has disappeared, it means we don't have to burn the bad coal. We can now burn the cleaner coal preferentially and leave the other stuff unburned. So 110 coal burning power stations start. And they are told that they have to reduce versus the 1980 value. They need to reduce their emissions by 50%. And we gave them 15 years to do it. So we looked at the value in 1980, which was at the tail end of the really bad years. It's already, I think it's probably already starting to improve by 1980. the 70s were bad. And then said, we're looking back at this. This is basically just unregulated, do whatever you want. And in 1995, we're saying 15 years from now, so this is in 1995, 15 years from now in 2010, you have to be twice as clean as the industry was 15 years ago. So 95 is in the middle. It's 15 years removed from 1980 and it's 15 years removed from 2010. And it worked. And so in the year 2000, they added, did I write this down? Yeah, I did. Oh, no. It is 2000. They added another 2,000 industrial sites. And I'm not sure, I didn't write down what the time limit on that is, but it's probably something similar of like, hey, you've got a decade. Reduce by an additional amount. And you can look around. So in 2010, they had reduced sulfur dioxide emissions to 9 million tons. That's a lot. We used to be twice that much. And the way that they did it is a couple of things that we've already seen. The plan utilizes this. Okay. We know of these things called scrubbers. Your calcium oxides, your calcium carbonates that will pull sulfur dioxide out of the smokestacks. Scrubbers go inside smokestacks and they pull impurities out before they're emitted. We get to use the low sulfur coal because the demand for coal has eradicated down to really small numbers. So now we don't have to use all the coal. We can be selective and use the low sulfur coal. We can switch to natural gas. Natural gas is lower in sulfur than the other fossil fuels. That's not a trivial thing. You can't just take a coal power station and flip a switch and turn it into a gas powered station. That requires a complete change of boiler design and the infrastructure of how to get the fuel to it. You could say, if you are a polluting object, you don't get to work all day, every day. I'm going to switch you off from time to time, and I'm going to cut your hours. And I think it's an EPA word that they use the word trim. I'm going to trim those hours. That seems to be an EPA word. Oh, and then here, this one's kind of, this is debatable. This one's kind of open for, wait a minute, they're doing what? The acid reduction treaty, or action reduction, not a treaty, what is it called? Isn't it T, A-R-T? I forgot. I think I had it a minute ago and now I've lost it. Acid reduction plan is the ARP. The acid reduction plan was the first plan that puts caps. So a cap says this is a number and you will not go above that number. When you get to this number, we're shutting you down. You can't exceed this value. That, you know, basically when you use all your money, there's no money left, I'm not going to bail you out. If you pollute, we're going to allow you to pollute to this value. We're not going to allow you to pollute over that value. Oh, I'm low for time. But you can buy offsets. And allowances. And so if I have two power stations and one of them is so clean, it's not emitting up to its cap, I can use that unused value on my other power station. And if they're both clean and they're both under their cap, I can sell you my unused allowance for pollution to you, the owner of the power station in the next town. Cap and trade. Very controversial when it came out because the trade part, I'm allowed to buy offsets and allowances, and they're tradable on the market in Chicago is the Mercantile Exchange. They're tradable on the Chicago Exchange. New York has the Stock Exchange. Chicago has the Mercantile Exchange. You can buy somebody else's emissions. And then something that's kind of super obvious. How about you just use less? What if we all just used less? Okay, I've gone a bit over. We started a bit late, so I'm taking that into account. Completely new topic when we come back. So we're done with all the atmospheric stuff, except for greenhouse gases, which are climate related as well. It's a separate part of the book. But now is a good place for us to put a line under this and set a piece of coursework to it.